All right, so now I want to take a look at how you can actually use finding inverses of matrices to actually solve equations. Now, look, if you're given the following equation, let's say something like this. Ax plus by equals c. And at the same time, you also want to solve this one. Let's call these ones a1, b1. And this is a2x plus b2y equals c2. Well, you could solve that using all sorts of sort of neat things we saw. Even Cramer's rule will work. But it turns out we can actually convert this to a matrix type thing. Because notice that, in fact, I could write a1, b1, a2, b2, and multiply that by just xy, and that equals c1, c2. Now let's think about that for a second and convince ourselves these really are the same thing. How do you multiply matrices? Well, you do this kind of thing. So this is a1 times x plus b1 times y, and that would have to be c1. Well, that's the first line. This says a2 times x plus b2 times y would equal c2. That's exactly the second line. So in fact, the whole cool thing about matrices is that if you have a whole bunch of systems like this of equations, many variables, turns out it's just one equation in matrices. These two things are identical. Don't believe me? Just multiply it out. And you see that these things are the same. Well, if I want to solve this, what would you do? Well, what you'd want to do is, that sort of looks like this. Suppose that's the matrix A. I call A this whole matrix right here. How would you solve this? Well, you just multiply both sides on the left by A inverse. And if you do that, what would happen? So if you multiply both sides on the left by A inverse, what you would see is, well, A inverse times A is the identity, so that just clears things off. And on the left, you just see this. So what that tells me is the following. If I want to solve an equation that looks like this, if I create a matrix A that's just the matrix of coefficients, A1, B1, A2, B2, just strip off those people, then the solution to this system, xy, will just be A inverse multiplied by these numbers. And that's the answer. Let me try to illustrate that with an example. Suppose I have the system minus x plus y equals 1, 2x minus y equals 1. How would I solve this using this system? What I would do is create a matrix A, which would just be the coefficients. So a minus 1, 1, 2, minus 1. And then the solution, xy, should just be A inverse multiplied by this, 1, 1. So what's A inverse? Well, let's find A inverse. Well, A inverse, how do I find inverses? I first take the determinant. That would be minus 1 times minus 1, which is 1, minus 2. So that's a negative 1. So I have 1 over negative 1. And then what do I do here? Well, I switch these things, which doesn't do much of anything. And I keep these but put negative signs in. OK, great. And now if I multiply through by this negative sign, I see that A inverse equals 1, 1, 2, 1. And you can check. Take that and multiply it by this, and you'll see that you get the identity. So therefore, the big finish is the following. What's xy? It just equals this matrix times 1, 1. So let's do that over here. What would I see? Well, so xy would equal, well, what's the first entry? Well, 1 times 1 plus 1 times 1, that's just 2. And what's the next entry? 2 times 1 plus 1 times 1, which is 3. And so this tells me that x must be 2 and y must be 3. You can check your answer. Let x be 2 and y be 3 here. 3 minus 2 is 1. That checks. If I take 2 times 4 and I subtract 3, I get 1. So in fact, this checks. So in fact, this really is the whole heart of the matrix theory. It allows us to take a whole bunch of equations, a system of equations in many, many variables, and basically compactify it into basically one equation in one variable, but all matrices. Then I'd solve it like any other equation. Just divide both sides by the coefficient. So if I divide both sides by A inverse, I would just see that xy equals A inverse that. And then all I got to do is go off, take that thing, which is a coefficient, but it's really a coefficient that's just a whole bunch of things. It's a matrix. Find its inverse, and then take its inverse and multiply it by this. It's the exact analog of this. Let me just show you exactly what we're doing here, because this is nothing weird going on here. Years ago, when we were kids, we'd solve this kind of equation. How would you do it? You'd multiply both sides by A inverse. And you'd see x equals A inverse times t. That's exactly what we're doing here. But now, this thing is no longer a number. It's now a collection of numbers. It's really a matrix. It's a grid of numbers that we now can actually have the power to find the inverse of. Once we have the inverse of it, we do the exact same thing as before. We just multiply it by this stuff, which turns out to be another matrix. And if we carefully do the matrix multiplication, we actually see what x equals and what y equals. So in fact, the real power behind matrices is that it allows us to take many equations in many unknowns and write it as just one equation in one unknown, but where the unknown, in fact, is a matrix and the coefficient in front of it is now also a matrix. So we sort of combined all the numbers into one big clump, combined all the variables into one big clump, and we have it equal to a big clump, and we solve the clumping using all the properties of matrices that we've seen. So in fact, that really is the heart of matrix theory and the power behind it. It allows us to take a hard problem and convert it into a simple problem, which we can then solve fairly reasonably. Anyway, the wrap up here is you have a whole bunch of equations like this, same number of equations, the same as unknowns. Then you just create the matrix of coefficients. And you can solve this by saying x and y equals the inverse of that matrix times these numbers here. Just compute the inverse very carefully, do a little matrix multiplication, you get x and you get y. All right, good luck and congratulations on sort of really nailing all the matrices stuff. Fine work. I'll see you up soon.